The transition metals are the largest group of elements in the periodic table. They are generally known for their hardness and their high densities, melting and boiling points. The group includes the 38 elements from scandium to zinc, yttrium to cadmium, hafnium to mercury, and rutherfordium to onunbium. The transition metals also include the 30 elements that make up the lanthanide and actinide series, but these elements are traditionally considered as separate subgroups. The most well-known transition metals are copper, silver, and gold. People have used these metals to make coins and jewelry for thousands of years. But many other transition metals are also important to society. The elements iron, nickel, and titanium are used in technology production, and many can be combined to create metal alloys that are vital for modern construction, commerce, and industry. The transition metals in general are hard, dense, and shiny. They have high melting and boiling points, and they are good conductors of heat and electricity. As with all metals, most are malleable and ductile, meaning they can be flattened into sheets or pulled into long wires without breaking. Transition metals share many traits, but the properties of individual transition metals can differ from one element to the next. For instance, only copper, silver, and gold are usually found in their pure metallic states. All other transition metals interact with oxygen in the atmosphere, so they're usually found only as compounds. The transition metals iron, cobalt, and nickel are the only 3 elements known to produce a magnetic field. These differences in chemical and physical properties may be better understood by taking a closer look at the periodic table. On the periodic table, the elements are listed in order of their atomic number. The atomic number represents the number of protons in an element's nucleus. In its normal or ground state, this nucleus is also surrounded by an equal number of electrons. As you read the periodic table from top to bottom, each horizontal line is called a period. Each period represents the number of electron shells the element's atoms normally have. For example, 4 electron shells are in an atom of titanium, so it lies in period 4. And an atom of hafnium in period 6 has 6 electron shells. The transition metals in period 7 are called transactinides because they come after the actinide series. All these elements are radioactive, and they can be produced only under unnatural conditions, such as inside nuclear reactors or high-energy particle accelerators. They are very short-lived. Some last for only seconds. As a result, scientists know little about these elements. As you read across the table from left to right, the vertical lines of elements are called groups. Elements in one group generally have the same number of electrons in their outermost electron shells. These electrons are called valence electrons. It takes 8 valence electrons to fill an outermost electron shell and make an atom stable. For most groups on the periodic table, the number of valence electrons an element has corresponds to its position on the table. For instance, hydrogen in group 1 has 1 valence electron, so it's very interactive. Beryllium in group 2 has 2 valence electrons and it's slightly less reactive. Boron in group 3 has 3 valence electrons, and so on. But the transition metals do not follow this pattern. These metals have valence electrons in 2 shells instead of just 1. Like other elements, the transition metals have electrons in their outermost shell. But they also have valence electrons inside this outermost shell, in an interior shell called a d orbital. The d orbitals hold between 1 and 10 additional valence electrons. When transition metals react with other elements, these partially filled d orbital electrons determine how the elements interact. Element number 21 on the periodic table is scandium. The atomic symbol for scandium is Sc. Scandium is a soft, silvery white metal. It tarnishes with air, burns when ignited, and dissolves in many acids. Scandium gets its name from Scandinavia, where it was discovered. Scandium is classified as a transition metal. It lies in the periodic table's fourth row, period 4. Each atom of scandium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of scandium, its nucleus has 21 positively charged protons, plus 24 uncharged neutrons. Scandium has 21 negatively charged electrons to balance its 21 protons. These electrons are found in 4 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, argon. Argon has 18 electrons distributed in 3 orbital shells. Scandium has 3 more electrons than argon. The first 2 electrons are found in the sphere-shaped 4s orbital. The final electron is found in one of 5 clover-shaped 3d orbitals. The electrons in both the 3d and 4s orbitals influence how scandium interacts with other elements. After a few drops of a liquid containing a scandium compound are introduced into a nearly colorless flame, we see a spectrum of colors. The heat causes the outer electrons to rise to a higher energy state. As they fall back to ground level, they emit a characteristic set of light wavelengths. This is the distinctive color we see. Neutron filters in nuclear reactors make use of scandium, and farmers use it to speed up the germination of seeds for crops. Scandium iodide goes into high-intensity lights to make harsh light look more natural for filming and in sports events. Element number 22 on the periodic table is titanium. The atomic symbol for titanium is Ti. Titanium is a hard, lustrous silvery metal, which is as strong as steel but 45% less dense. Titanium is named for the Titans of mythology, who were known to be incredibly strong. Titanium is classified as a transition metal. It lies in the periodic table's fourth row, period 4. Each atom of titanium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of titanium, its nucleus has 22 positively charged protons, plus 26 uncharged neutrons. Titanium has 22 negatively charged electrons to balance its 22 protons. These electrons are found in 4 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, argon. Argon has 18 electrons distributed in 3 orbital shells. Titanium has 4 more electrons than argon. The first 2 electrons are found in the sphere-shaped 4s orbital. The remaining 2 electrons are distributed among 2 of 5 clover-shaped 3d orbitals. The electrons in both the 3d and 4s orbitals influence how titanium interacts with other elements. Although titanium is a very strong metal, it is much lighter than steel. This is demonstrated when the weight of a titanium crowbar is compared to that of a steel one. When a second titanium crowbar is added, the combined weight is still lighter than that of one steel crowbar. Titanium is used in chemical plants, replacement joints, aircraft engine fan blades, and spacecraft components because of its strength and light weight compared to steel. Titanium dioxide is used as a non-toxic white pigment for paint, plastic, paper, ceramics, food coloring, ink, and lipstick.
Element number 23 on the periodic table is vanadium. The atomic symbol for vanadium is V. Vanadium is a corrosion-resistant silvery white metal that is soft and pliable. Vanadium gets its name from Vanadis, the Scandinavian goddess of beauty. Vanadium is classified as a transition metal. It lies in the periodic table's 4th row, period 4. Each vanadium atom consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most common form of vanadium, its nucleus has 23 positively charged protons, plus 28 uncharged neutrons. Vanadium has 23 negatively charged electrons to balance its 23 protons. These electrons are found in 4 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, argon. Argon has 18 electrons distributed among 3 orbital shells. Vanadium has 5 more electrons than argon. The first 2 electrons are found in the sphere-shaped 4s orbital shell. The remaining 3 electrons are distributed among 5 clover-shaped 3d orbitals. Since the electrons in the 3d shell are at a lower energy than those in the 4s shell, only these 2 electrons will influence how vanadium interacts with other elements. Vanadium tarnishes easily in moist air and turns black. This protective film of oxide on the surface makes it resistant to corrosion. This metal does not react with alkalis, but is attacked by concentrated acids. Here, vanadium crystals react with concentrated nitric acid, a strong oxidizing agent. This oxidizes the vanadium crystal, which goes through a series of oxidation states. The ion in the second oxidation state is responsible for the blue color change seen in the test tube. Nitrogen oxide gas is produced in this dynamic reaction and effervesces in the solution. Because it is highly resistant to corrosion, vanadium is added to iron alloys and steel to make axles, car gears, and jet engines. Vanadium's compounds are also used to permanently fix dye to fabric and to create very conductive magnets. Element number 24 on the periodic table is chromium. The atomic symbol for chromium is Cr. Chromium is a very shiny bluish-white metal that is brittle and non-corrosive. Chromium is never found uncombined in nature. Chromium gets its name from the Greek word chroma, meaning color. Chromium is classified as a transition metal. It lies in the periodic table's 4th row, period 4. Each chromium atom consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of chromium, its nucleus has 24 positively charged protons, plus 28 uncharged neutrons. Chromium has 24 negatively charged electrons to balance its 24 protons. These electrons are found in 4 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, argon. Argon has 18 electrons distributed among 3 orbital shells. Chromium has 6 more electrons than argon. The first electron is found in the sphere-shaped 4s orbital shell. The remaining 5 electrons are distributed among 5 lobe-shaped 3d orbitals. The electrons in both the 3d and 4s orbitals affect how chromium interacts with other elements. This demonstration shows the common chromium plating process using electrolysis. A variety of metal objects strung on a metal frame are removed from a hot bath of diluted acid, removing all traces of dirt for a smooth, even finish. The frame is then lowered into a bath of chromium salts, where a low DC voltage is applied to the objects. The thin wires attached to the objects make electrical contact, and an electrochemical reaction begins to take place. The chromium ions become metal and are deposited on the surface of the objects. After 30 minutes, the voltage is turned off and the objects are removed and cleaned, showing the shiny metallic finish of chromium. Because chromium is hard and corrosive resistant, it is often used in making stainless steel and other steel alloys. Chromium is used as plating for knives, tools, car parts, and safes. Chromium is also responsible for the color in rubies and emeralds. Element number 25 on the periodic table is manganese. The atomic symbol for manganese is Mn. Manganese is a gray-white or pinkish metal that resembles iron, but it is harder and more brittle. Manganese gets its name and atomic symbol from the Latin word magnes, meaning magnet. Classified as a transition metal, manganese lies in the periodic table's fourth row, called period 4. Each atom of manganese consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most common form of manganese, its nucleus has 25 positively charged protons, plus 30 uncharged neutrons. Manganese has 25 negatively charged electrons to balance its 25 protons. These electrons are found in 4 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, argon. Argon has 18 electrons distributed among 3 orbital shells. Manganese has 7 more electrons than argon. The first 2 electrons are found in the sphere-shaped 4s orbital shell. The remaining 5 electrons are distributed among 5 clover-shaped 3d orbitals. The electrons in the 3d shell are at a lower energy than those in the 4s shell, so they are actually contained within the 4s shell. As a result, generally only the 2 electrons in the outermost 4s shell influence how manganese interacts with other elements. In this experiment, manganese dioxide is shown reacting with concentrated hydrochloric acid to produce chlorine gas. This is a standard method of producing chlorine in the laboratory. The chemical reaction involves an intermediate compound, manganese tetrachloride, and water, which then breaks down to form manganese chloride and chlorine gas. The escaping chlorine gas can be seen as faint yellow-green bubbles. This reaction demonstrates the variable chemical states that manganese and most other transition metals can have. Almost 90% of the manganese produced every year is used in steel manufacturing. Manganese is also used to make dry cell batteries, or it's added to paints as a drying agent, or to ceramics and glass to give them a green color. This is a United States Nimitz-class nuclear-powered aircraft carrier. It is the largest, most powerful, and most capable aircraft carrier class in the world. This floating airbase holds 6,000 people and 80 state-of-the-art airplanes. Construction of an aircraft carrier represents the world's most complex shipbuilding challenge. And it all begins with steel. Steel is created by adding carbon to molten iron ore. When iron is heated, the crystal structure of its molecules spread out and can absorb the smaller molecules of carbon. As the iron cools, the carbon is trapped within the iron molecules, creating a much stronger metal, steel. But the steel used for building an aircraft carrier must be exceptionally strong. So steel alloys are used. Metal alloys are combinations of metals and other elements that are engineered to have specific properties that the metals alone lack. The elements chromium, manganese, and vanadium can be added to steel to create steel alloys that improve certain characteristics of the steel. Adding chromium, a shiny, corrosion-resistant metal, to steel creates stainless steel. When the chromium is added to the steel used in making armor plating for a ship's hull, it bonds with the carbon deep inside the thick plates and makes them harder, less brittle, and more resistant to corrosion. Manganese is an essential element for making steel because it interacts with sulfur. Atoms of manganese have 2 extra electrons in their outer shell, while those of sulfur lack 2. As a result, when manganese is added to steel, it bonds with the sulfur in the mixture to eliminate or reduce sulfur's weakening effects, which makes armor plates stronger, harder, and longer lasting. Vanadium is another important alloying metal for carrier steel. But unlike chromium and manganese, vanadium is not used for making armor plating. Instead, vanadium is added to steel to resist metal fatigue, which is repeated pressure that causes metal to gradually stretch out of shape. Because it is so good at helping steel hold its shape, vanadium is added to crankshafts, gears, springs, and jet engines, where very high strength and abrasion resistance are critical. It takes 7 years to build a single Nimitz-class carrier. But when the ship is finally complete and taken to sea, it is one of the most powerful aircraft carriers on Earth, and a testament to the ingenuity of its makers and the strength of its steel.
Element number 26 on the periodic table is iron. The atomic symbol for iron is Fe. Iron is a dark gray metal that was known to the ancients. The Latin word ferrum gives iron its name and atomic symbol. Iron is classified as a transition metal. It lies in the periodic table's 4th row, period 4. Each atom of iron consists of a cloud of electrons surrounding a compact nucleus that contains almost all of the atom's mass. In the most common form of iron, its nucleus has 26 positively charged protons, plus 30 uncharged neutrons. Iron has 26 negatively charged electrons to balance its 26 protons. These electrons are found in 4 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, argon. Argon has 18 electrons distributed among 3 orbital shells. Iron has 8 more electrons than argon. The first 2 electrons are found in the sphere-shaped 4s orbital shell. The remaining 6 electrons are distributed among 5 clover-shaped 3d orbitals. The electrons in the 3d shell are at a lower energy than those in the 4s shell, so they are actually contained within the 4s shell. As a result, generally only the 2 electrons in the outermost 4s shell influence how iron interacts with other elements. In this experiment, aluminum metal is combined with iron oxide to produce a stream of molten steel. The mixture of iron oxide and aluminum is ignited with a burning sparkler, and the energy released causes the metals to melt until a pool of molten iron forms. This process is called the thermite process. It was invented more than 100 years ago to make strong welds between metals, such as when molten iron is poured between the rails of a train track to form a permanent weld. Very large amounts of iron are used to make steel, which is one of the most widely used metals in the world. Plants and animals also need iron, since it is a key component of chlorophyll and hemoglobin. The iron in hemoglobin helps carry oxygen through the bloodstream in humans and animals.
Element number 27 on the periodic table is cobalt. The atomic symbol for cobalt is Co. Cobalt is a lustrous silvery metal with a faint blue color. Cobalt's name comes from the German word Kobold, meaning imp or gremlin. Cobalt is classified as a transition metal. It lies in the periodic table's fourth row, period 4. Each atom of cobalt consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of cobalt, its nucleus has 27 positively charged protons, plus 32 uncharged neutrons. Cobalt has 27 negatively charged electrons to balance its 27 protons. These electrons are found in 4 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, argon. Argon has 18 electrons distributed in 3 orbital shells. Cobalt has 9 more electrons than argon. The first 2 electrons are found in the sphere-shaped 4s orbital. The last 7 electrons fill the clover-shaped 3d orbital. The electrons in both the 3d and 4s orbitals influence how cobalt interacts with other elements. Cobalt is ferromagnetic, like iron, but with only 2/3 of iron's magnetic strength. Its magnetic property is visible when pieces of metal are placed on a wooden surface and are attracted to the magnet. Cobalt can maintain its magnetism at very high temperatures, up to 1,130 degrees Celsius. Thanks to its magnetic properties and its color, cobalt has a variety of applications. It goes into industrial magnets and alloys for use in the aerospace industry. Cobalt-60, a radioactive isotope, is used in cancer radiation treatment. Artists use the element to produce blue color in ceramics, stained glass, and jewelry. Irradiating a diamond with cobalt-60 will turn it blue. Element number 28 on the periodic table is nickel. The atomic symbol for nickel is Ni. Nickel is a lustrous, silvery, malleable, and ductile metal. Nickel's name comes from the German word Kupfernickel, meaning devil's copper. Nickel is classified as a transition metal. It lies in the periodic table's fourth row, period 4. Each atom of nickel consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of nickel, its nucleus has 28 positively charged protons, plus 30 uncharged neutrons. Nickel has 28 negatively charged electrons to balance its 28 protons. These electrons are found in 4 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, argon. Argon has 18 electrons distributed in 3 orbital shells. Nickel has 10 more electrons than argon. The first 2 electrons fill the sphere-shaped 4s orbital. The final 8 electrons are found in the clover-shaped 3d orbital. Since the electrons in the 3d orbital are at a lower energy than those in the 4s orbital, only the 2 valence electrons in this 4th level shell influence how nickel interacts with other elements. Nickel metal is ferromagnetic, meaning that it exhibits spontaneous magnetism. The balls of nickel in a wooden bowl are attracted to a magnet. Nickel is commonly known for making coins. It is a major component of stainless steel, which is an alloy of iron, nickel, and chromium. Nickel is resistant to corrosion, so it is used in gas turbines and rocket engines. Most nickel is used to make alloys, creating materials with unique properties.
Element number 29 on the periodic table is copper. The atomic symbol for copper is Cu. A reddish-brown metal, copper oxidizes to form a green oxide. The name copper is derived from the Latin cuprum, the name for the Greek island of Cyprus where copper was mined. Copper is classified as a transition metal. It lies in the periodic table's fourth row, period 4. Each atom of copper consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of copper, its nucleus has 29 positively charged protons, plus 34 uncharged neutrons. Copper has 29 negatively charged electrons to balance its 29 protons. These electrons are found in 4 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, argon. Argon has 18 electrons distributed among 3 orbital shells. Copper has 11 more electrons than argon. The first electron is found in the sphere-shaped 4s orbital. The next 10 electrons fill 5 clover-shaped 3d orbitals. While copper should have 2 electrons in the 4s orbital, the atom is more stable if one of these electrons instead is used to fill the d orbital in the third shell. This flexibility in electron structure influences how copper interacts with other elements. A wire-pulling die with a series of reducing diameters increases the length of copper wire from 10 inches to 15 inches as it is simultaneously thinned. Beeswax applied in between each draw provides lubrication. Copper is an excellent conductor of electricity and heat, making it useful for electrical equipment and cookware. Along with silver and gold, it's a metal commonly used in coins. Copper is also a component in alloys such as bronze when it was used for making knives and swords, brass for plumbing, and gunmetal for weapons. "24 centuries ago, China was torn by conflict. In the period known as the Warring States, the authority of the Zhou dynasty faltered, and a dozen upstart kingdoms struggled for dominance. The battle for supremacy was as much a struggle over resources and technology as it was a test of military might. Bronze was a main figure in these struggles. The Warring States period occurred at the height of China's Bronze Age, when metalworking had become a high art. Bronze is an alloy of copper and tin, but it melts at a lower temperature than copper, and it's stronger than copper, so it's more valuable for tools, weapons, and other objects. By the 5th century BC, the Chinese were using bronze for all of their weaponry and important ritual objects. Historians knew the importance of bronze to the ancient Chinese, but they had no idea of their skill with cast bronze until a major archaeological discovery. In 1977, workers in the Hubei province in central China were in the process of raising a hill to build a factory. They uncovered the tomb of a ruler who had lived in the 5th century BC. Buried with him in the tomb was a magnificent set of 64 bronze bells.
When we removed the bells and other metal objects from the tombs, we verified that most objects were in bronze and the name Zhuyi were inscribed on them. Zhu is the name of the state. Hu is nobility title meaning marquis. Yi is his name.
The bells revealed a level of unprecedented skill.
One of the most impressive features of these bells is the fact that one bell can emit 2 different sounds, a low tone in the center and a higher tone on the edge. This was a tremendous technological achievement in the 5th century BC, and one, in fact, which modern bell makers have found very difficult to imitate.
It must have taken centuries of trial and error for craftsmen to figure out how to cast a bell with the two desired notes.
These craftsmen who cast the bells were not some dusty guys in a violin shop, but they were probably the most advanced technicians of their age, possibly comparable to supercomputer engineers or nuclear physicists of our age.
But it wasn't just the skill of the bell makers that impressed archaeologists. The amount of bronze in the bells vastly outweighed the amount in the marquis' weapons, armor, and chariot fittings. The bells appeared to have had an importance beyond entertainment. More likely, they played a central role in ceremonial rituals involved in ancestor worship. The blessings of ancestors were more important to Chinese rulers than military strategy or weaponry.
Because the bells, through their powerful music, are able to reach across the divide and speak to the ancestors. The Marquis' ancestors were dead, but they were not gone. They remained very important. They could punish him, they could reward him. They could help him maintain his power, they could take it away. He had to demonstrate his gratitude to them, because not only did they give him his body and his life, but they gave him his fiefdom.
And it was in that context that the music was performed on the instruments, and that these many splendid ritual vessels that were discovered in the same tomb were also used. And they were simply the most important thing that a state could have. They embodied the authority of the state, and therefore it was appropriate to expend any amount of resources the state had at its disposal on the manufacture of such object.
With the unification of China in 221 BC, the era of the warring states came to an end, and the importance of ancestor worship and ritual music began to wane. The significance of these bells shifted from the religious to the scientific as they continued to reveal secrets of Bronze Age China.
Element number 30 on the periodic table is zinc. The atomic symbol for zinc is Zn. Zinc is a bluish-white brittle metal with a low melting point. The name zinc comes from the German Zink, which may come from the Persian word sing, meaning stone. Zinc is classified as a transition metal. It is located in the periodic table's fourth row, period 4. Each atom of zinc consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of zinc, its nucleus has 30 positively charged protons, plus 34 uncharged neutrons. Zinc has 30 negatively charged electrons to balance its 30 protons. These electrons are found in 4 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, argon. Argon has 18 electrons distributed among 3 orbital shells. Zinc has 12 more electrons than argon. The first 2 of these electrons are found in the sphere-shaped 4s orbital shell. The next 10 electrons fill 5 clover-shaped 3d orbitals. Since the electrons in the 3d orbitals are at a lower energy than those in the 4s orbital, only the 2 valence electrons in this 4th level shell influence how zinc interacts with other elements. Zinc is a gray metal with a pronounced blue tinge. Here, zinc balls are melted and the crust removed. The molten zinc is then used to create animal shapes in a mold. The metal is non-toxic and has a low melting point, which makes it suitable for casting various shapes. Zinc is most commonly used for galvanization, a process that coats another metal object with a layer of zinc to prevent corrosion. Zinc is also used to make dry cell batteries and die castings. Brass, an alloy of zinc and copper, is used in many household objects. Zinc is also alloyed with lead and tin to make solder, a metal with a low melting point used to join other metallic items. Zinc oxide is often found as a white pigment in paints and cosmetics. Element number 39 on the periodic table is yttrium. The atomic symbol for yttrium is Y. Yttrium is a soft silvery white metal that has a highly crystalline structure. It is stable in air due to an oxide film that forms on its surface. Yttrium is named for the town of Ytterby, Sweden, where the element was first found. Yttrium is classified as a transition metal. It lies in the periodic table's 5th row, period 5. Each atom of yttrium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of yttrium, its nucleus has 39 positively charged protons, plus 50 uncharged neutrons. Yttrium has 39 negatively charged electrons to balance its 39 protons. These electrons are found in 5 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, krypton. Krypton has 36 electrons distributed in 4 orbital shells. Yttrium has 3 more electrons than krypton. The first 2 electrons fill the sphere-shaped 5s orbital. The final electron is found in one of the 5 clover-shaped 4d orbitals. The electrons in both the 4d and 5s orbitals influence how yttrium interacts with other elements. When an yttrium disk is cooled with liquid nitrogen, the yttrium's electrical resistance is reduced to 0 and the disk becomes a superconductor. A superconductor will repel any magnet brought near it. This is known as the Meissner effect. Normally, one magnet will attract another magnet with the opposite pole and repel a magnet with the same pole. What is unique about the Meissner effect is that the yttrium is not actually a magnet. It repels this gold-coated neodymium magnet like a mirror. The yttrium mimics neodymium's magnetic poles so that the same magnetic forces are reflected back and the magnet is kept in suspension. Yttrium oxide is used for making superconductors because it conducts electricity without losing energy. It can also be added to camera lenses to make them more resistant to heat and shock. Yttrium aluminum garnet is used in high-intensity lasers. The element also has many useful alloys. When it is added to cast iron, the metal becomes more workable.
Element number 40 on the periodic table is zirconium. The atomic symbol for zirconium is Zr. A hard, gray-white metal, zirconium is highly resistant to corrosion. Zirconium is named for its main source mineral, zircon. Classified as a transition metal, zirconium lies in the periodic table's 5th row, period 5. Each atom of zirconium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of zirconium, its nucleus has 40 positively charged protons, plus 50 uncharged neutrons. Zirconium has 40 negatively charged electrons to balance its 40 protons. These electrons are found in 5 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, krypton. Krypton has 36 electrons distributed among 4 orbital shells. Zirconium has 4 more electrons than krypton. The first 2 electrons are found in the sphere-shaped 5s orbital shell. The second 2 electrons are distributed between 2 of 5 clover-shaped 4d orbitals. The electrons in both the 4d and 5s orbitals influence how zirconium interacts with other elements. From the 1960s through the 1980s, most photographic flash bulbs contain zirconium. A zirconium flash bulb is taken from its packaging and placed into position with a clamp stand. The blue-tinted glass bulb, filled with pressurized oxygen, also contains a thin tangle of zirconium. A 9-volt battery ignites the zirconium, and the combustion produces an exceptionally bright light. Flash bulbs like these could be used just once because the zirconium is consumed in the reaction and the heat shatters the glass bulb. Because zirconium is a corrosion-resistant metal, it is commonly used in high-performance pumps and valves, and as an alloying agent in steel. Because it does not readily absorb neutrons, it is also widely used for fuel rods in nuclear reactors. Zircon is a zirconium compound that is frequently used in jewelry because it can take on the appearance of diamonds. Another compound, zirconium carbonate, is added to lotions that treat poison ivy. Since the 1950s, nuclear power has been essential to meeting the world's energy demands. The 104 licensed nuclear reactors operating in the United States generate about 20% of the country's electrical energy. Nuclear reactors have a core of radioactive material which releases heat. Water running past the core absorbs the heat and turns into steam. The steam moves a turbine in a generator, creating electricity. Then the steam cools into liquid water and flows back toward the core to begin the cycle again. The water prevents the core from overheating, and it transfers heat energy from the reactor to the generator. Nuclear fission, the source of the reactor's heat energy, is the process of using a neutron to split a single atom into two smaller atoms, releasing free neutrons and energy. In a nuclear reactor, the free neutrons split other atoms in the reactor core. The released heat powers the electrical generator. Most reactors use uranium-235 as the energy source. The uranium is processed into pellets, which fill hollow fuel rods. The rods are made of zircaloy, a zirconium alloy that is at least 98% zirconium. Zirconium will not melt in the heat generated by uranium fission, and it does not absorb neutrons, so it will not interfere with the chain reaction. 90% of all zirconium produced by the United States is used in nuclear reactors. When enough uranium is present in the reactor core, the fission process becomes a self-sustaining chain reaction, with the neutrons released by one atom causing another atom to split. Due to their high radioactivity, nuclear power plants require extensive safety measures for the workers and people living nearby. Workers don protective suits when they are working close to the reactor core. Control rods are inserted into the reactor core to maintain the speed and energy of the chain reaction. These rods are similar to fuel rods, but they are not radioactive and they absorb neutrons. Accidents at the Chernobyl and 3 Mile Island nuclear reactors slowed the development of nuclear power in the United States. But as technology helps improve the handling of radioactive materials, nuclear power may become a more noticeable source of energy.
Element number 41 on the periodic table is niobium. The atomic symbol for niobium is Nb. Niobium is a shiny steel gray metal that forms a bluish-purple oxide. This is a strip of very pure electrolytic niobium crystals. Niobium is named after the mythical Greek figure Niobe because niobium is very similar to tantalum, named for Niobe's father, King Tantalus. Niobium is classified as a transition metal. It lies in the periodic table's 5th row, period 5. Each atom of niobium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of niobium, its nucleus has 41 positively charged protons, plus 52 uncharged neutrons. Niobium has 41 negatively charged electrons to balance its 41 protons. These electrons are found in 5 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, krypton. Krypton has 36 electrons distributed among 4 orbital shells. Niobium has 5 more electrons than krypton. The first electron is found in the spherical 5s orbital shell. The remaining 4 electrons are distributed among 4 of the 5 clover-shaped 4d orbitals. The electrons in both the 4d and 5s orbitals influence how niobium interacts with other elements. Used to make jewelry, niobium shimmers with iridescent colors because an oxide forms on its surface. It is one of the least reactive metals, so it is widely used in ear piercing because it very rarely causes a reaction with the skin. Niobium is a common material in stainless steel alloys for nuclear reactors, jets, missiles, cutting tools, and pipelines. Niobium alloyed with zirconium, tin, or aluminum goes into specialized wire necessary for superconductive magnets. Superconductive niobium cavities are essential to the operation of some electron accelerators used to study the structure of matter.
Element number 42 on the periodic table is molybdenum. The atomic symbol for molybdenum is Mo. Molybdenum is a hard, lustrous, silvery white metal. Molybdenum's name comes from the Greek word for lead, molybdos, because the element was often mistaken for lead. Molybdenum is classified as a transition metal. It lies in the periodic table's 5th row, period 5. Each atom of molybdenum consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of molybdenum, its nucleus has 42 positively charged protons, plus 56 uncharged neutrons. Molybdenum has 42 negatively charged electrons to balance its 42 protons. These electrons are found in 5 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, krypton. Krypton has 36 electrons distributed in 4 orbital shells. Molybdenum has 6 more electrons than krypton. The first electron is located in the sphere-shaped 5s orbital. The final 5 electrons are found in the clover-shaped 4d orbitals. The electrons in both the 4d and 5s orbitals influence how molybdenum interacts with other elements. Molybdenum is usually produced and sold as a gray powder because as a bulk metal, it has the high melting point of 2,623 degrees Celsius. Molybdenum is used in the alloy moly steel because it has advantageous properties, such as maintaining its strength up to 2,000 degrees Celsius. This thermal property is demonstrated when a molybdenum bolt is heated using an oxyhydrogen torch. The bolt glows white hot and does not melt. Under the same heat, the steel bolt generates intense sparks, melts, and droops. Moly steel is used in manufacturing automobile, aircraft, and rocket engines. Other molybdenum alloys go into heating elements and radiation shields, and they support wire filaments in light bulbs.
Element number 43 on the periodic table is technetium. The atomic symbol for technetium is Tc. Technetium is a radioactive silvery metal that occurs naturally in uranium ores. Technetium's name comes from the Greek word techniktos, meaning artificial. Technetium is classified as a transition metal. It lies in the periodic table's 5th row, period 5. Each atom of technetium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most stable form of technetium, its nucleus has 43 positively charged protons, plus 55 uncharged neutrons. Technetium has 43 negatively charged electrons to balance its 43 protons. These electrons are found in 5 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, krypton. Krypton has 36 electrons distributed in 4 orbital shells. Technetium has 7 more electrons than krypton. The first 2 electrons fill the sphere-shaped 5s orbital. The remaining 5 electrons are found in the clover-shaped 4d orbital. The electrons in both the 4d and 5s orbitals influence how technetium interacts with other elements. A technetium compound is used as a radioactive tracer in bone scans. Technetium solution is injected into a patient's arm. After a few hours, the bone absorbs the technetium, and a camera reading varying levels of radioactivity scans the bone. In a normal scan, the technetium is distributed evenly throughout the bone. Areas of high or low radioactivity may indicate bone injury or disease, and additional tests can be done to determine possible causes. All of technetium's isotopes are radioactive. It is primarily used for laboratory experimentation and medical diagnosis.
Element number 44 on the periodic table is ruthenium. The atomic symbol for ruthenium is Ru. Ruthenium is a lustrous silvery metal. It is named after Ruthenia, the Latin term for Russia. Ruthenium is classified as a transition metal. It lies in the periodic table's 5th row, period 5. Each atom of ruthenium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of ruthenium, its nucleus has 44 positively charged protons, plus 58 uncharged neutrons. Ruthenium has 44 negatively charged electrons to balance its 44 protons. These electrons are found in 5 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, krypton. Krypton has 36 electrons distributed in 4 orbital shells. Ruthenium has 8 more electrons than krypton. The first 2 electrons fill the sphere-shaped 5s orbital. The remaining 6 electrons are found in the clover-shaped 4d orbital. The electrons in both the 4d and 5s orbitals influence how ruthenium interacts with other elements. Ruthenium is one of the hardest transition metals. A Shor durometer is used to compare the hardness of tin and ruthenium. The tin reads as moderate, between 60 and 70 units. But ruthenium is so hard that the meter goes off the scale. Ruthenium is often used in jewelry and lab tools. It is also combined with titanium to make deep water pipes resistant to corrosion.
Element number 45 on the periodic table is rhodium. The atomic symbol for rhodium is Rh. Rhodium is a rare silvery hard metal. Rhodium's name comes from the Greek word rhodon, meaning rose-colored. Rhodium is classified as a transition metal. It lies in the periodic table's 5th row, period 5. Each atom of rhodium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of rhodium, its nucleus has 45 positively charged protons, plus 58 uncharged neutrons. Rhodium has 45 negatively charged electrons to balance its 45 protons. These electrons are found in 5 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, krypton. Krypton has 36 electrons distributed in 4 orbital shells. Rhodium has 9 more electrons than krypton. The first 2 electrons are found in the sphere-shaped 4s orbital. The remaining electrons are located in the clover-shaped 5d orbital. The electrons in both the 4s and 5d orbitals influence how rhodium interacts with other elements. Rhodium is mainly used in catalytic converters for cars because it is excellent at reducing emissions of nitric oxide and carbon monoxide. A catalytic converter cut in half reveals 2 internal honeycomb filters. The rhodium catalyst rips the nitrogen atom out of a nitrogen oxide or dioxide molecule and holds it, freeing the oxygen. The nitrogen atom bonds with another nitrogen atom already on the catalyst and is released as a gas. When heated by a propane torch, the rhodium absorbs oxygen from the atmosphere and forms an unstable oxide. In this state, rhodium can catalytically convert the propane gas from the unlit torch to carbon dioxide. The conversion is an exothermic reaction, which is how the propane burns without a flame from the torch. In addition to catalytic converters, rhodium goes into mirrors and reflectors in headlights. It is also used as a catalyst in the production of chemicals.
Element number 46 on the periodic table is palladium. The atomic symbol for palladium is Pd. Palladium is a lustrous silvery white malleable ductile metal. Palladium is named after Pallas, the Greek goddess of wisdom. Palladium is classified as a transition metal. It lies in the periodic table's 5th row, period 5. Each atom of palladium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of palladium, its nucleus has 46 positively charged protons, plus 60 uncharged neutrons. Palladium has 46 negatively charged electrons to balance its 46 protons. These electrons are found in 4 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, krypton. Krypton has 36 electrons distributed in 4 orbital shells. Palladium has 10 more electrons than krypton. While palladium should have 2 electrons in the 5s orbital, it is more stable if all 10 of these electrons fill the clover-shaped 4d orbital. This complete 4th level shell determines how palladium will interact with other elements. Palladium has the unique ability to absorb more than 900 times its volume of hydrogen gas at room temperature. In this experiment, a test tube is filled with water, and a palladium strip on a wire is placed at the bottom. The test tube is then inverted and placed into a bowl of water. Hydrogen gas is bubbled into the test tube, which displaces half the volume of water. The water level is marked and the test tube is left to stand. As time passes, the water level rises until it covers the palladium strip, which has absorbed the hydrogen gas. Palladium is very useful for the separation, purification, and storage of hydrogen. In the chemical industry, it is used as a part of a catalyst in the production of nitric acid for fertilizers. It is also used to coat electrical contacts in switches, for magnetic springs in clocks and watches, and in jewelry, where it is alloyed with gold to form white gold.
Element number 47 on the periodic table is silver. The atomic symbol for silver is Ag. A reflective precious metal, silver tarnishes after it's been exposed to air for a long time. The element's name comes from Selphor, an Anglo-Saxon word for the metal. Its symbol stems from the word argentum, the Latin name for silver. Silver is classified as a transition metal. It lies in the periodic table's 5th row, period 5. Each atom of silver consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of silver, its nucleus has 47 positively charged protons, plus 60 uncharged neutrons. Silver has 47 negatively charged electrons to balance its 47 protons. These electrons are found in 5 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, krypton. Krypton has 36 electrons distributed among 4 orbital shells. Silver has 11 more electrons than krypton. The first electron is found in the sphere-shaped 5s orbital. The next 10 electrons fill 5 clover-shaped 4d orbitals. While silver should have 2 electrons in the 5s orbital, the atom is more stable if one of these electrons instead is used to fill the d orbital in the 4th shell. This flexibility in electron structure influences how silver interacts with other elements. Solid silver is very malleable, ductile, and has a brilliant white lustrous appearance. Here, skilled silversmiths are working the metal to make a necklace. They cut, drill, file, and solder it. Silver is a popular metal for use as jewelry, coinage, and household objects. Because it is one of the best reflectors of visible light, mirrors, jewelry, and decorative household items are often made with silver. Pure silver is an excellent conductor of heat and electricity, so it is a main ingredient of solder, and it's common in electrical contacts. Compounds of silver are used in photography and high-capacity batteries. In 1861, the United States faced a crisis. Several southern states had seceded from the Union, threatening to tear the country in half. President Lincoln was facing a long and expensive war. He needed every resource at his disposal. And one such resource lay in the wilds of the newly formed Nevada Territory. In 1859, prospectors had found gold in the western part of what is now the state of Nevada, just east of the Sierra Nevada mountains. But soon, miners discovered that true wealth was in the blue sand mixed in with the gold deposits. It was a rich silver ore. As news spread, seasoned prospectors and inexperienced hopefuls converged on what became known as the Comstock Lode. The sudden wealth of Nevada did not go unnoticed in Washington, D.C. With war looming, the government moved to make Nevada a Union territory in early 1861, securing its riches for the North. As more and more people trekked to western Nevada, mining towns sprang up overnight. But getting to the silver ore was difficult because it lay deep underground. New technology developed rapidly to gain access. Many men and women looked to profit from the droves of people hunting for wealth. As towns grew, businessmen and women catered to the needs of the miners, creating fortunes for themselves. By the 1880s, the Comstock Lode was exhausted. prospectors moved on to other mineral strikes, including the Klondike Gold Rush in Canada. But even gold was not as influential as the Comstock silver, which made fortunes, led to the rise of an industrialized mining industry, and helped the North win the Civil War.
Element number 48 on the periodic table is cadmium. The atomic symbol for cadmium is Cd. Cadmium is a toxic silvery metal that is soft enough to be cut with a knife. Cadmium's name comes from cadmia, the Latin word for calamine. Cadmium was discovered as a byproduct of heating calamine. Cadmium is classified as a transition metal. It lies in the periodic table's 5th row, period 5. Each atom of cadmium consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of cadmium, its nucleus has 48 positively charged protons, plus 66 uncharged neutrons. Cadmium has 48 negatively charged electrons to balance its 48 protons. These electrons are found in 5 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, krypton. Krypton has 36 electrons distributed in 4 orbital shells. Cadmium has 12 more electrons than krypton. The first 2 electrons fill the sphere-shaped 5s orbital. The remaining 10 electrons fill the clover-shaped 4d orbital. Since the 4d orbital is completely filled, only the 2 electrons in the 5s shell influence how cadmium interacts with other elements. A ball of cadmium is placed into a hydraulic cutter. When freshly cut, cadmium is a bright silver color. After a few hours in the air, it tarnishes and becomes gray. Cadmium's main industrial use is to electroplate steel. A thin film of the element provides protection against corrosive environments. Another common use is in nickel-cadmium rechargeable batteries. Cadmium is sometimes a component of nuclear control rods because it is good at absorbing neutrons.